Testing, 1, 2, testing. Testing, 1, 2, check.
Good evening. Welcome to Netflix. I'm Brooks from our cloud security organization here at Netflix, and I'm super happy to have the meetup group back on our campus for what I think is going to be some really cool talks. And I'll now ask Clarence to introduce our first speaker.
Thanks, Brooks. Yeah, so this is the second time that Netflix is hosting us. So thanks very much to Brooks, because it's the second time he's helping to put this together. This is our 11th meetup, so it's been a lot of work trying to put these together. And if any of you work in companies that are related to this area, like security and data science in general, then feel free to reach out to me. I think hosting a meetup is a great way to just get your name out there and just show the world what you guys are doing. Um, so I won't take up too much of your time. There's some stuff by O'Reilly at the back. Currently, I'm working on an O'Reilly book with Dave Freeman at LinkedIn, and it's on pre-sale on Amazon now. The name is Machine Learning for Security. So if you're interested in that, feel free to talk to me about it after that. Just grab me anywhere. But let's get started now. The first speaker is Rekha from Netflix, and I'll let her take it from here. Thank you.
Better now? Okay. So today I'm going to talk about Trainman, which is our detector of security threats as they unfold in a corporate environment. A little bit about myself. My name is Rekha. I'm part of cloud security here at Netflix. My interests lie at the intersection of security and machine learning. In the past, I've applied machine learning in other system contexts, done adversarial machine learning and distributed systems. So with that, let's get started. I want to start with how does the landscape in threat landscape for employee security look like? A recent report by Sky High Networks stated that 3/4 of the organizations face one version or other of compromised accounts. Over 90% of the, or almost 90% of the organizations experience one or more insider threats. And about half the companies see data exfiltration each month. Yes, the problem is severe, but why do we care, and what sort of impact it has on the company? So the first one is lower productivity. So if there is a compromised user account, and let's say you detect it, the simplest thing you will do is reset users' credentials, ask them to get a new device, but it's a painful and tedious process. It can lead to loss of trust and safety in your work environment, brand damage, and eventually lost revenue over a period of time. So given this landscape and the potential negative impacts of it, what are some of the key entities in your corporate environment that are at risk because of this? The first one is a diverse conglomeration of entities that I call corporate assets, which is your infrastructure, data, the various enterprise apps that are running in your system. The second class of entities is the users and the devices that they use to connect to your or interact with the corporate environment. For the purposes of this talk, I'll be focusing only on the compromised users or the at-risk users and devices and their interaction thereafter in the corporate environment. So what are the typical scenarios of this particular at-risk users and devices? Let's look at some of the most common one. First one is that of an accidental misuse or a careless user where the user doesn't realize, but they deleted one of the sensitive files or deleted the AWS private key or something. Yes, it's a big mistake, but you know that it's an inadvertent one, hopefully easy to recover from. The second class is slightly more serious, where an attacker takes control of a user's account or a system. This would be an example where a user was misled through a phishing attack, or it could be like somebody actually exploiting a vulnerability on your device. The third, and probably the scariest of all, is that of a malicious insider. Say if an employee goes rogue, how do you detect it? Again, for the purposes of this talk, I'll be focusing only on the compromised users and how do we go about detecting those scenarios. So what does a compromised user activity look like, or what do we mean by it? We start with the scenario that I mentioned. An attacker has taken control of a user's system. One of the many things they could do is steal the user's credentials and then use them to access something in your corporate environment, whether it's a sensitive app or a data. And our goal as part of Trainmen is to detect such an activity and drive appropriate security action. One of them could be we alert the user saying, hey, is this you doing this, or is it somebody else? Or it might be informing the security team saying something suspicious is happening in our environment. So this is the use case that I'm going to go dig deeper into and drive. The rest of the talk will be focused on it. So let's start with what is the vision of Trainman. So Trainman is an emerging set of capabilities that identify security events by analyzing user behavior and activity and drive appropriate security action. So taking a step deeper, it comprises of four main components. The first one is the actual user activity. So it captures and ingests this user activity into a warehouse. Then this activity is fed to a set of detection tools wherein we decide if any of the activity present in there is suspicious or not. And if there is some suspicious activity, then we decide what is an appropriate action based on the risk of it. Again, the action could be informing the security team, the user, or asking for a second authentication factor from the user. Finally, every time we do take an action, we capture the response as well and feed it back to our warehouse with the hope that eventually we'll use this to improve our detection models. But before I go any further, there are a bunch of challenges that we had to face in order to solve this problem or attempt to solve this problem. The primary one is that of sparsity. I think most people working with data science and security, it's not usually a big data problem, especially when it comes to user activity. The second is, and the biggest of all, is that of a ground truth. There are not enough examples of the actual suspicious activity that you want to catch. Also, you don't know what are the the possibility of suspicious activity is potentially infinite. Third is that of false positives. Now, in a different recommendation or an ML-based system like Netflix, let's say we predict, oh, this is the movie you're going to like, put it on the first row, and if you don't like it, it's bad, but it doesn't, the impact is not that high compared to if we say that a user's activity was suspicious and we actually say block the user from doing something, but it was actually a legitimate event. That impact is much higher and more severe. Finally, explainability. I want to talk a little bit about it. Is typically most data scientists, including me, if we run the data through a bunch of models and we get high accuracy, say 95%, we are super happy about it. It's like, oh, here is a model, plug into it, you get the results out of it, don't bother me afterwards. But in security, that's not enough, because if the models are opaque, the analyst sitting at it or the security team actually taking action based on that is at a complete loss. So what do we do about these challenges? To deal with sparsity, we take the common approach of using aggregates if they are feasible or fit the use case. We do strategic filtering. For ground truth, we ended up injecting synthetic events in the form of red tests. So we actually inject various suspicious or malicious activity scenarios in our data. The third is we added an extra step as a post-processing step after our modeling phase, which is the correlation engine. We use correlation engine to inject business logic as well as a broader security context to avoid false positives. The final one, to address the explainability issue, we created Analyst UI, where there is enough, not only that you have information about what events were predicted to be suspected, but also enough additional context about it. As for example, what was the user doing around the same time when this specific event was tagged to be suspicious. So with this high-level approach, let's look at the overall architecture of Trainman. So here's the user going by their day, doing the tasks for the day. We capture all of that activity into a security data warehouse. In addition to capturing the raw events, we also add a bunch of enhancements and enrichments. For example, what is the user's role or which org are they part of? If there is an IP information, we try to get the geodata for that IP and so on and so forth. So what ends up in a warehouse is an enriched version of the actual activity. Then we pass this activity through a conglomeration of models, our machine learning pipeline and the correlation engine, and the anomalies are then written back to the warehouse. Next is what you see at the bottom is a set of action modules that we have. So we have three classes of action that we take today. One is automated response, which could be an additional factor or an automated SMS or an email to a security personnel. There's a security analyst using the Analyst UI, looking at all the events that we have tagged or considered to be anomalies, and they look at manually. When I go to the UI, you'll understand that it's not as tedious as it sounds, because that's the reason for having that UI. And finally, there is an email notifier where for the high fidelity anomalies, we send out an email notification to the user saying, hey, we saw something suspicious about you. Was that really you? And then the users are encouraged to go to our internal tool called Stethoscope. This has been recently open source, where a user gets information about what is the security status of their devices and is what all activity by the user has been considered suspicious or not. Finally, if the user responds, we capture that feedback and put it back into the warehouse. So in summary, we collect user activity from many apps and put it in the warehouse. We learn the typical user behaviors using machine learning and statistical analysis. And using the same analysis, we score the user activity, pass it through a correlation engine to figure out what's the priority and if it's truly an anomaly or not, and drive appropriate action for it. So this was a slightly deeper overview of it. Now let's get into the actual modules of it. I'll start with the security data warehouse, which is our central location. The goal for our warehouse was to standardize data ingestion. have a single source of truth, have a consolidated schema across different data sources. That way, the data scientist who is sitting and analyzing the data, they don't have to read from different tables, different schemas, and tune accordingly. It also enables us to do unified curation of data sources. As I mentioned, say adding geodata, user info, other metadata to the events. And finally, that's also our home for common dimension tables that we have. So the simple goal for having the warehouse was to enable consistent and sophisticated analysis with minimal reinventing the wheel. So what kind of user activity do we capture? So we capture both the authentication logs as well as the application logs wherever it's relevant. These are discrete events in a Netflix system, and we capture activity for all users and all apps in our ecosystem, and then apply metadata to it. To give you a sense of what's the scope of the problem in terms of data, we have hundreds of apps, thousands of users, and millions of events that Trainman today deals with. I agree, if there are big data people here, they will be smirking at it as like, this is not a big data problem, but it is what it is. So here's a snapshot of what the user activity looks like. Say a user tries to access some of the corporate assets. They go through some form of authentication, and we capture these logs. So as you can see, for each actor, there is a user agent string, which is, say, representative of their device. There's a resource that they're trying to access, the IP address, the geodata, and the actual action that they're trying to take. So now that we have all the data ingested and in a reasonable shape, let's look at what kind of analysis can be done on it. So our first goal in terms of behavioral analysis is to figure out if there are any unexpected accesses. And what do we consider the symptoms of these? The first one is if the access is from an unknown device. Is it from an untrusted location, at an odd time of the day, or if the actual resource that they're trying to access is what they shouldn't be doing. And to transform these high-level indicators into features, this is what we do. So for each like user agent string, we have a notion of what the device is it a trusted device or not, what location the access is coming from, the timestamp. We also capture past history of resource access. So if an app A gets accessed at, say, midnight every day or not, does the user typically access this particular app at a given time or day or not? Finally, for each users, we maintain a list of trusted devices and locations that we typically see access from. So for instance, if you're accessing from within the company or at home, the activity is probably your typical activity, because that's how you typically access corporate assets. And finally, we maintain a manual list of each application and their criticality for it. Now let's go to the models that we have for this. I mentioned the sparsity. So we group events by user and the apps, because we don't have enough events per app for every user. And we compute the top user app groups for it. And everything that doesn't fit in this top, we have like a catch-all group for them. Then for each and every group, we train a separate supervised model for it. And for each of those groups, we also have a personalized threshold. In a minute, I'll explain how we compute that threshold. So once we have these models per group, we score the events, the incoming events, and decide if the event is expected or not. So here is an example of how we personalize the threshold. So this is a simple ROC curve. On the x-axis is the false positive rate. On the y is the true positive rate. The red line is the linear intercept that we try to tune for each group and figure out what is the best threshold for that particular group. So these thresholds are tuned dynamically every time we train, and we train our models once a day. The goal is that we'll find accesses or events that have very low probability of occurring, and those will be tagged as anomalies. Here are examples of some of the we have had with this system. The first one is, this was actually a funny case where a good deed ended up being wrong. This was a case where a Netflix employee helped their neighbor set up a Wi-Fi network. Given the age and the lack of tech savviness of their neighbor, the network was insecure, and the Netflix user didn't realize they were hopping onto that network. Given that they'd set it up, they had access for it. And we suddenly started seeing access from this employee from an insecure network. And when we flagged him, he was like, oops, I didn't know this. So this was a case of accidental misuse. We don't try to aim for these, but these sort of come free when we try to go for compromised users. For the specific compromised user cases, we have run a bunch of red team tests by synthetically injecting, say, cookie theft and replay, and certain atypical access of high priority apps. And we've been reasonably successful with those. The next goal for this set of models is to identify unusual activity. Now, how is it different from unexpected access? There's a small difference. In the first case, we are trying to see if you should have accessed something or not. The second is, given certain accesses, what we want to understand is if the pattern of access is unusual or not. So in this case, we are actually looking more at aggregate data. So for instance, we look at if the volume of activity that we see from a user for a given resource is unusual. The way we derive this is we look at the past behavior. So we have a running set of features for each user of what is their typical volume, what are the typical actions that they take for each of the resource. If the resource in this case ends up being a file, then we also have a notion of what are the good practices for sharing patterns. And if we see any deviation there, then that would be another indicator. So the methodology we use here is twofold. One is a simple one, which is volumetric based, wherein we have statistical models for every user, action, and resource to see if they've crossed a certain threshold. Note that this threshold is tuned for every user action combination. The second, which is the more interesting one, is the behavioral patterns. Here today what we have is a statistical model for sharing patterns. So it's like you typically don't share something outside of Netflix, but you started sharing it, or you suddenly shared 80% of your file corpus that you have with an external user. So that would indicate to us is if the user has been compromised or there is a deliberate attempt of data exfiltration. The ML-based models to detect these patterns are still a work in progress. So what have we achieved with what we have with the volumetric and the behavioral statistical models? For volumetric, we were able to find high number of deletes and downloads by certain users. Some of them were innocuous, some of them were actually malicious, and we were able to take action for it. The second one was more behavioral, where we saw atypical account sharing or document sharing. And the third was an employee planning to leave suddenly had abnormal activity patterns, like they started sharing their documents with their personal email address or downloading a whole bunch of sensitive documents that they otherwise didn't access. So these are the results, and I've gone to the results before talking about the correlation engine, just to give you a sense of what it is, but some of these results were achieved after the correlation engine step. So what does the correlation engine do, and what's the purpose of it? So the first thing it does is it combines output from various models and updates the priorities of these anomalies. So for instance, if, say, I had unusual, unexpected access and also unusual activity, then the anomalies related to me would, say, become a higher priority because there's something really wrong going on in my system. And it's worth checking what that is. We take into account, the correlation engine takes into account some notion of past user behavior and other anomalies that are in play. It can also filter out low confidence anomalies to help with the false positives. For example, let's say the security team recommended folks in the company saying upgrade to the new version of the browser because there's a critical security fix coming in. Now, if everyone goes about going and upgrading their browser, their user agent string changes and we see a whole bunch of unknown device access. The correlation engine is smart enough to figure out if the change in your user agent is actually because of a browser upgrade or is it a totally different device. And it will take drive appropriate action based on those things. So finally, the Analyst UI. So this is a snapshot of how the Analyst UI looks at it. The top chart that you see is basically the number of anomalies that are there on a given day. This one shows for past 7 days. There are a bunch of knobs wherein the analyst can change this by looking at it, say, just today, last 3 days, different time periods. The lower half gives the details of what the anomalies is. What's the timestamp of the event, who the user is, what is the application, what's the priority based on the model plus the correlation engine, and have we already emailed that anomaly and have we received any feedback for those anomalies. Furthermore, the analyst can actually click on a specific anomaly or for a specific user and get a bigger context about it. So on the right, you see a bunch of activity from the user for which we had an anomaly, what other things were happening within a certain time frame. Also, in the lower right corner, you see the recent alerts that have been emailed to this user. On the left, you see more information about the actual anomaly or the event itself is. What was the IP? For this user, what are the trusted IPs and user agents that we have on account, and so on and so forth. So this will give the analyst a sense of why the anomaly was, why an event was considered to be an anomalous event, and the action that was proposed by the engine. The analyst can override that action or do a additional follow-up with the user. So in summary, we have gotten encouraging initial results with the system. Having a centralized data warehouse was a necessary first step, and it saved us a lot of pain. Appropriate post-processing helped us reduce some of the false positive rates and easily integrate some of the business logic or a broader security context without having to tweak all the models in the finest granularity. The UI has been super useful to increase the analyst productivity and in general showcasing this tool and across the company. And there are still many gaps in coverage and methodology that we have to bridge. One of the things that is on our in the most recent future is to leverage the user feedback that we have gathered from this to improve the accuracy of our models. So I'll take questions. If none of your questions are answered, you can always email us on the Trainmen external users at Netflix group. Okay, I'll repeat the question. The question is, what do we use for location data? So we use a bunch of resources right now. One is we derive it from IP, and we have a bunch of external vendors that we use to gather geodata for IP.
So no.
It's purely IP as of now.
Can you catch the mic?
Can you go into a little bit about your data warehouse? You were saying your data warehouse, the tables, and what are the fields that you capture on that one?
So I'll go on.
Yeah.
So this is a good representation of the fields we have. Like for each event, we usually have a notion of an actor, who the actual user performing that action. There are separate tables that will have information about this user that is not event specific. The user agent string is typically our device information. We also have the application information, and then there are dimension tables that will say if the application is critical or not, who owns that application, so on and so forth. Similarly for IP address and the action itself.
I actually have two questions. The first one is, have you ever considered use those false positive examples and retrain your model? Maybe, like increase the weights in the cost function so that you can avoid those kind of false positive examples.
Yeah, yes. Yes, the first step we do is actually to see if the model itself hasn't been tuned, and we take every care to tune the model.
Yeah.
But even after tuning it to the best possible scenario across months, there will still be some false positives. And to overcome those, we have the additional rules in place.
The other question is about how you use the UA string information. So basically, you kind of extract some of the information from UA string to serve as the features in the machine learning model. Have you ever considered use like word vectors, something like that, that captures the entire string information from that?
Could you repeat?
Like, have you ever considered using word vectors, which is basically representing that string and all the tokens inside of it as a numerical vector, and use that as your features to predict, anomalies?
No, we haven't. We do parse the string and put them into separate tokens, like if it's an OS part, browser, OS version, and so on. But we haven't mapped them to, say, numerical or hashed vectors, hashed features.
Thanks.
So the question is, how much time does my system have to detect if an event is anomalous or not? So today we do it in a batch mode, and we have a lag of about 4 hours before we detect something is bad or not.
If someone in switches teams, is your system configured to send an alert, or how does it work? Does it have some integration with HR systems or something like that?
Could you please repeat? I'm not sure I heard you right. It's integration with what? So
No, I mean, if someone, an employee switches teams, so he will have access to a different resource now in a new team. Is your system configured to know that, or it will send an alert?
Yes and no. So yes, in the sense that we do maintain a dimension table about an employee, like for every user we know what their role is. So when the role changes, that dimension table will get updated and we'll have this information. But it might take a while for we don't do any explicit retuning or trigger explicit retuning because of that. It might learn it over a period of time. So the question is Trainman specific to web apps, or is it applicable to any apps? It is applicable to any apps. Okay, so the follow-up question is if the application is not web-based and there is SSH activity trying to delete some sensitive files or move some sensitive files, what do we do? So that is where I mentioned the second part of it is unusual activity. Even if you say you have missing piece of, in this case, the user agent string or something, which kind of makes this appear more to be web-based, but in essence, that is one of the many features that we have, and that's why we have that second set of models on purely activity-based. Sort of is, you might be coming from the trusted network. It could be you could be sitting in office using your assigned and trusted device and the trusted IP, the Ethernet port that you usually use, but if your activity itself is unusual, and it has deviated from what you have done in the past, then that would get flagged by the system.
I had a question, but so kind of a follow-up on the last one. Say a privileged user is spearphished, and so their device is compromised, and they're logging in from home the way they usually do, except it's not really them. and it's not an unusual time, and they're privileged users, so the files they normally access are sensitive files. Do you have any way you would imagine that would stand out to your correlation engine?
So one would be the activity volumes or some of the patterns that I was talking about. So today, we don't necessarily catch that action very well unless you cross a certain threshold of volume in terms of it, or if you start sharing it outside. But that's why, as I said, we have a learning-based model that we are working on specific use case of that, where a privileged user has been compromised, and to see if what kind of deviations we see in their activity.
Okay, can you give more details about the models you use?
What kind of details?
Like if you use supervised learning, what model is, or if you are using other.
Okay, sure. So the first step where we do group events by user snaps, that's a pure volume-based grouping. If there is a certain amount of volume for that combination, we consider it to be a cluster. For the supervised part, we use random forest classifier to predict if an event is expected or not. Then at the correlation engine level, we use user and app affinity. So we have the alternate least squares method to figure out a user and app affinity. In that case, let's say I predicted an event to be anomalous because you access an app that you typically don't. But given other users who have similar activity to you, they access that app. In that case, the affinity of that app to you, by virtue of you being similar to those other users, is high. In that case, the priority might go down. And the converse is true as well, where if you access an app, it's a low priority anomaly based on the model, but it sees that you have really low affinity to that app. In that case, the correlation engine might bump up the priority of that anomaly to be tagged.
Does the correlation engine assign any value to the asset? Like, for instance, if someone was accessing a movie file versus, say, marketing data?
Today, we don't do it by asset, but we do have a notion of sensitive data. And if whatever is considered sensitive data, that does change the priority of the anomaly.
Has your HR department approached you yet on developing models for highly effective employees?
Highly effective employees?
Yes. Not yet. Not yet. Okay.
Who is this to? Hi, Rekha. I had a question about sort of building your supervised models using the data. And you mentioned you rely on a number of things. You rely on, I guess, historical data from users within the organization, as well as red team events. One thing that I guess came in my mind when you mentioned that is there's always this possibility when you're collecting data to build a model that you might encounter selection bias, that the process by which you actually collect the data is very representative of what you're trying to fit to. What steps, if any, do you take to reduce the chance of selection bias in your data sets?
That's an excellent question. So today, we do look at the bias. So for instance, we change the weights accordingly. So if there are synthetic events, we modify the weights. Unfortunately, the process is manual today, where we actually look at what selection we have done, how is the distribution. We do have a bunch of audits around if the shape of the data has changed. And we do investigate all of those changes, but it's manual today. We don't have an automated way of adjusting to the bias.
I'm interested in the way how you connect the data. The example you gave is you can find out someone is using unsecured AP. So do you have any agent running in the user notebook, or everything is connected at the server side?
Everything is collected at the server side. There is nothing running on client devices. In Netflix, there is no policy of managed systems. We do have some managed devices, but that's not a practice. I could tomorrow just buy a laptop from Apple Store or from Best Buy and bring it, and I can be connected to the network.
Hey, Rekha. Do you currently, or do you have any plans to share suspects with any law enforcement agencies?
I'm not sure I can answer that question. I think if law enforcement comes asking for, I'll leave it up to our legal team to decide what they can or cannot share.
Generally, police don't ask you if you've been compromised. You have to tell them.
I would probably let Brooks answer that question.
Brooks.
Sure. If it's something illegal that we needed to involve other companies or law enforcement, I think we'd do that. I don't think we've had too much interest from the community of like knowing what we're doing with machine learning and stuff and needing to, coming to us for information, but we would certainly reach out if it was something useful and we could use their help.
Have you tried to use different machine learning algorithm or model to make sure that your data is not overfitting other than random forest?
Oh, yes. We tried with a bunch of them, like the prominent culprits like logistic regression, linear regression, SVM sort of thing. We zeroed in on random forest because it gave us the best results. And we do tune our models daily, retrain our models daily.
Hello. Okay. So this thing turns off in flight, so you don't have the wind sound. But anyone else have questions? Else, let's give a big hand to Rekha. Thank you. So next up, we have Ting Fan from DataVisor, who will be talking about the latest fraud trends. Just give her a couple minutes to set up.
Thanks. Thanks.
Oh, you can use that? Yeah.
Cool. Can you hear me? Great. Really happy to be here. My name is Ting-Fang Yen. I'm a research scientist at DataVisor. Just a little background on me. I started out my career working in data analysis for security applications, and I've worked in malware detection and enterprise security for a number of years, and now I work in fraud detection. So just a very brief overview about the company. So we're a security company, been around for a little over 3 years. We provide a full stack analytics platform for detecting fraud, abuse, and money laundering activities within consumer facing online services. And to date, we've analyzed activities over 1.3 billion users and processed over 500 billion events. And some of our customers include some of the largest social, financial, and mobile gaming companies in the world. So this talk is really about fraud. And online fraud and abuse has really evolved a lot in the past decade or so, becoming much more diverse and sophisticated. And one of the reasons for this is that these online services that we use every day have also evolved a lot in recent years. Things used to be somewhat single function. Like you go to Dell.com to buy laptops and that's it. But today, these services are becoming these feature-rich platforms that have a blend of social networking, messaging, gaming, e-commerce, and online to offline service attributes. You can think of Facebook as a classic example in this space. They have posts or walls of user-generated content. They have games you can play with your friends. They have likes that signal social reputation. They have ads that show up on your newsfeed. And more recently, they have peer-to-peer selling marketplaces. So as these online services introduce more features onto their platform, the attack surface also grows. And as they develop more ways to monetize their user base, the fraudsters are also finding more ways to cash out on the online services. And there are already many reports of these newer fraud attacks in the news. For example, people conducting fake purchases and writing fake reviews to artificially boost a product or sell its ranking. People creating fake Uber driver accounts and using GPS spoofers to simulate rides in order to collect driver bonus and promotions. Fake listings on Airbnb that try to lure renters off of the platform into under-the-table and potentially unsafe transactions. Bots, and most times human laborers too, faking app installs and clicks and app engagement even to try to take a chunk out of the advertiser's budget. Gamers harvesting virtual currency that can be later resold or traded for profit. Reward points and loyalty programs that are stolen and then converted into merchandise or services that are worth real money. Not to mention the various types of financial fraud and transaction fraud that continues to happen as a result of data breaches and stolen credentials. So these fraud attacks are costing services millions of dollars a year, but not all of them are exploiting vulnerabilities in the service. Writing a review is a perfectly valid action on a social network. Never mind, it's a fake review somebody paid me to write. So these fraudsters are really just abusing available features for financial gain. And to do this, all they need is to create user accounts or compromise existing users, even better. And that will give them all the access they need to conduct their attacks. They also have a lot of ways to try to evade detection. So for example, they can use traffic anonymizers like public cloud services, VPNs, or other types of proxies to hide their actual network location. And new services, new cloud service or new proxy services are coming up all the time, such that blacklisting or reputation-based systems are hard to maintain and they expire quickly. The fraudsters can also use device flashing or virtual machines to simulate the appearance of hundreds or thousands of unique devices. So every user comes from a unique device, which can potentially defeat device fingerprinting. And these fake accounts, they can have very realistic looking profiles. They have friends, they have pictures, they have posts on their profile, mostly likely scraped off the profiles of other legitimate users. So that can make content-based detection challenging. And lastly, the attackers often age the fake accounts, sometimes for months or years before using them in an attack. So this helps the fake accounts stay under the radar. Sometimes older accounts are viewed as having better reputation by some systems. And also at the same time, the dormant accounts can be used for testing out the attack in small batches before launching the actual attack. And in our observation, 44% of the fraudulent accounts sleep more than 7 days before attacking. So after seeing a lot of attacks like this, we really wanted to understand more about online fraud and about how they conduct their attack operations. And in an attempt to do so, we analyzed over 500 billion applicational events collected from multiple global online services spanning social networks, financial services, and mobile gaming apps. So our global telemetry network collects these anonymized signals, which include IP addresses, mobile device types, user agent strings, email domains, phone number prefixes, across our client database as collected by our analytics service. And so in this talk, I will describe the results that we got from analyzing data collected during the second half of 2016. And during the 6-month period, we observed 410 million IPs, 5.3 million user strings, 3.6 million email domains, and these other data listed here. And by analyzing all these signals together, we wanted to understand more about the operations of the fraud operation, and more specifically, the anatomy of an online fraud attack. So we know that to conduct an attack, the fraudster needs a machine, or need a set of machines to base their operations on or run their scripts off. There has to be some operating system or software installed on those machines with internet access. And they need to be able to connect to these online services that they're targeting, potentially through multiple proxies. And when they create fake accounts on the online service, they need to supply certain information, like user nicknames or email addresses. And they need to decide how many fake accounts they want to create and how and when to use those fake accounts in an attack. So I'm going to try to follow this flow and talk about each of these steps in more detail. So let's look at device platform first. In general, most users access online services from mobile devices. Wireless communication is ubiquitous, and there are many online services have mobile-specific features that makes it really convenient to use these apps, like features like finding nearby attractions on your phone, the ability to take and upload pictures, or other features that leverage mobile sensors. But what about fraudsters? What kind of platforms do you think they use? What do you think is the percentage of fraudulent accounts coming from a desktop machine versus those that come from a mobile device? Does anybody have a guess? 100% what? PC. Actually, very, very close. So in our data, we see 82% of the fake accounts come from desktops, and 18% come from mobile devices. This figure shows the distribution of the device platform among fraudulent accounts. Windows alone accounted for 78% of the fake accounts. So why is this the case? Why do you think fraudsters like desktops? Yeah, well, I think the title of the slide also kind of gives away our answer, but in general, it does seem a little easier to commit fraud on desktops as opposed to mobile devices. For one, there is no reliable fingerprint that can be used to track web users. You can clear cookies, you can log out your account, and there can be multiple hosts and users behind the same NAT box, so they have the same IP. It's also very easy to run emulation software on desktop machines to simulate the appearance of hundreds or thousands of unique devices and unique users. By contrast, mobile apps sit directly on the device itself, and so they have the ability to collect more detailed device information to create more accurate device fingerprints. They can also monitor user activities within the app, so it might make the fake accounts a little bit harder to evade detection. So now what if we focus on the mobile device platforms and compare Android versus iOS? What do you think is the ratio in the number of fraudulent accounts coming from an Android device compared to an iOS device? And what do you think is the ratio in the fraud rate on Android versus iOS? 90-10. I'm talking to a very sophisticated crowd here. So in our observations, the ratio in the number of fraudulent accounts, Android to iOS is 3-to-1, and the ratio of the fraud rate is 8-to-1. So I'm interpreting to be, if you see a user from an Android device, it's 8 times more likely to be fraudulent than a user coming from an iOS device. So this kind of ties back to our previous slide about taking the path of least resistance. Android is an open source platform, and you can customize a lot of things on Android machines and add new features. And there are also many more apps available for Android compared to iOS. And some of these apps are designed specifically to spoof your GPS location, to forge network requests, to automate human-like activities, or other functionalities that's convenient for fraudsters. But even though it seems easier to commit fraud on desktops and Android machines, sometimes the fraudsters have to operate off iOS devices. Maybe they're trying to do ad fraud. So the install or the click has to come from an iPhone device. Or maybe they're targeting specifically the iOS version of an app. So since it's much harder to emulate iOS devices, the fraudsters often have to actually own an iPhone in these cases, or own a set of iPhones, which can get very expensive very quickly. So this figure shows the distribution of iPhone models across all iPhone users and across all fraudulent iPhone users. The x-axis here is the iPhone model sorted according to the model's release date, with the older ones to the left. And now if you just look at the black line alone, corresponding to all iPhone users, you can see that the most popular models are the iPhone 6 and 6 Plus. However, fraudsters seem to have a preference for older models, like the iPhone 5, 5C, and 5S. These three models accounted for 2/3 of the fraudulent iOS users. So considering that like the latest iPhone, the 7 Plus, I think it starts at over $700 each, it does seem a little bit more cost effective to use older models, especially if you want to create an army of fake accounts. These figures shows a similar thing, but for the mobile device operating system. The figure on the left corresponds to Android, and the figure on the right corresponds to iOS. And again, the x-axis is the operating system version, sorted according to the release date, with the older ones to the left. And we're seeing a very similar thing here compared to the iPhone models. The fraudsters are lagging behind normal users. If you look at Android, most users are on Lollipop or later, but 77% of the fraudulent accounts are on KitKat or Jelly Bean. Similarly, for iOS, half of the fraudulent iOS users are on iOS 9, while most users have moved on to iOS 10. It could be that these newer operating systems have better security features that makes it harder for the fraudsters to run some of their tools. Or it could be just they're running older devices, so they can't run newer operating systems sufficiently. So now let's look at the location of these fraudulent accounts. If we focus on the fraudulent accounts that are created on online services based in North America and in Europe, where are those fraudulent accounts coming from? Yeah, this map shows the countries hosting the most number of fraudulent accounts and the percentage out of all fraudulent accounts. The top 3 countries we see, US, China, and Vietnam. I was a little surprised to see Vietnam, but my coworkers said they're not surprised. But now if we look at these fraudulent accounts targeting China-based online services, it's a very different picture. 95% of the fraudulent accounts on China-based services come from within China. And this map shows the provinces hosting the highest number of fraudulent accounts. Kind of interesting to see that most of the coastal provinces are highlighted. And I asked my coworker from China, like, why is this the case? And she said, it's just like how Florida has a lot of fraud. I don't really know what that means, but from this map, I'm interpreting it to be like there's larger population along coastal areas, and so there may be a presence of fraud communities, at least in those areas. But these network locations of the fraudsters can be kind of misleading. The fraudsters can use traffic anonymizers to hide their actual network location, and they often do that using public cloud services. Cyber attackers already have a history of using the cloud to host their attack infrastructure. In 2009, attackers hosted a command and control server for the Zeus botnet on Amazon EC2. And since then, the cloud has been used to host exploit servers for web drive-by download attacks, web pages and SEO spam, and also in advanced persistent threat attacks to distribute malware or to store stolen information from data breaches. It's not hard to see why they choose the cloud to host their attack infrastructure. It is extremely affordable. Here you can see that DigitalOcean, Amazon, and Linode all have basic packages. So you can get 512 gigabytes of RAM, 20 gigs of storage, and a terabyte of bandwidth for $5 a month. That's only $0.0075 an hour. Extremely affordable. Now here's a quick stat. what do you think is the percentage of user accounts that originated from a cloud service IP address that are fraudulent? 30%? A little high, but close. So in our data, we see 18% of the accounts that are hosted in the cloud are fraudulent. And these figures show some trends of these cloud-hosted attacks over the past year. Figure on the left is the fraction of accounts that are hosted in the cloud, that's originated from a cloud service IP that are fraudulent. And figure on the right is the fraction of fraudulent accounts that originated from the cloud. So in both cases, there's an upward trend, and indicating that cloud adoption is increasing among fraudsters. And if you look at the latest data point on this graph from the end of March of this year, 44% of the accounts that were hosted on the cloud are fraudulent, and 13.5% of fraudulent accounts are hosted in the cloud. These figures show the cloud services that are hosting the highest number of fraudulent accounts. Now, Amazon EC2, there's already a history of attackers using Amazon EC2 for fraud. Like I've talked about botnet command control servers and exploit servers for web drive-by downloads. So it may not be surprising that we also see a lot of fraudulent accounts being hosted on AWS. But in this figure, you can see that some of the services have a very high percentage of fraudulent accounts, and some have a relatively low percentage. I don't know exactly why this is the case, but I suspect that it's due to the pricing model at these services, and maybe related to how easy it is to sign up new accounts at those services. So some servers may require an email address, a phone number for text verification purposes, and a valid credit card all at sign-up time. So this may create friction that the attackers would want to avoid. But different crime rings appear to use different cloud services as well. So here we separate our user accounts into two categories. Those that are registered in China-based online services, and those that are registered in global online services. So this figure shows for each cloud service, the fraction of user accounts that are hosted at that service that are fraudulent, for accounts registered in China-based services in orange and global online services in black. Now, if you just look at the first set of bars on the left corresponding to AWS, it means that 50% of the accounts that's hosted on AWS and registered in China-based online services are fraudulent. While this is true for only 9% of the accounts on global online services. So in general, it seems that cloud is abused to a greater extent in China. The orange bar is almost always higher than the black bar. Since cloud adoption is still relatively rare, especially among consumers in China, I'm suspecting it's likely that those who do use the cloud are using it for some suspicious activities. But now if we look at fraudulent accounts that originated from an IP address in the US, so just looking at US fraudulent accounts, then we find 39% of them are hosted in the cloud. Since most of these online services in our data set are based in the US, but the fraudsters can come from anywhere in the world. So for these fraudsters that are outside the US, that are offshore, they may want to launch their attacks from the US in order for their fake accounts to look more legitimate. But if we look at the fraudulent accounts detected on different online service verticals, then we again see a big difference in the types of networks they use. So for example, 54% of the fraudulent accounts on social networks are hosted in the cloud. But this is true for only 13% of the fraudulent accounts on financial services. Instead, the majority of fraudulent accounts on financial services come from residential IP addresses. This is likely related to the nature of these attacks. So social networks are targeted by massive waves of fake account registration attacks that are made scalable by the cloud. But financial attackers are much more stealthy, launching their attacks through a combination of scripts and some manual work. In fact, if we look at the sizes of these fraud attack campaigns on different online service verticals, we can see that the attack campaigns on social networks are 17 times bigger on average than those on financial services. So social attacks are orchestrated this way, likely due to the economics of fake reviews and spam. So in order for them to be profitable, they have to launch hundreds of thousands of these attacks on the social network, which need a massive number of fake accounts to do this. Now, by contrast, fraud attacks on financial services are much smaller, since the profit margin is much higher on financial platforms. Now let's look at the information supplied by the fraudsters when they register fake accounts. So email addresses is one of the most common and often the only piece of information you need to register an account on an online service. There are plenty of email services to choose from, but the most popular ones among fraudsters are Gmail, Outlook, and Yahoo, just like normal users. There is a very small percentage of fake accounts that registered using throwaway emails. So these are email services that allow users to receive messages at a randomly generated temporary email box instead of giving out their real email. Or originally used to prevent spam, the convenience of these services are also attractive to fraudsters. They can use the temporary email box to receive account confirmation messages at account sign-up time, bypassing the need to register email addresses in advance. Now, even though most of the fraudulent accounts register with a popular email domain, the extent to which they do this differs across online service verticals. Fake accounts on financial services are much more likely to register using a reputable email domain, while fraudulent accounts on social networks are more likely to use a somewhat obscure domain, often a domain that the attackers registered for the purpose of creating these email accounts in bulk. Now, this figure shows the cumulative percentage of fake accounts that register with an email address from one of the top 10 email domains in our data set, for fake accounts registered on financial services and for fake accounts registered on social platforms. If you just look at the last data point in this graph, the last data point to the right, 72% of the fake accounts on financial platforms register with an email address from one of the top 10 email domains. Well, this is true for only 45% of the fake accounts on social networks. Now, I mentioned briefly at the beginning of this talk that one of the ways the fraudsters evade detection is to age their fake accounts, sometimes for months or years before using them in an attack. And this helps the fake accounts stay under the radar, and they can also be used to test attacks in small batches before launching the actual attack. And we saw that 44% of the fraudulent accounts sleep more than 7 days before attacking, and 37% sleep more than 90 days. But this sleep duration of the fake accounts really varies depending on how the fake account is going to be used eventually. So accounts used in social engineering attacks tends to have a longer sleep time compared to those used in financial attacks. And this is probably because in order for these social attacks to be successful, they need a certain degree of trust from the victim. And having an older account can make the fake account look more legitimate to other users. Now, by contrast, financial attacks, they are more time constrained, since these financial information like stolen credit cards or banking information can expire very quickly. Here's an example of an actual sleeper cell attack that we saw in the wild. Here, the attacker's goal is to spam users on the social network in the form of posts. So here you can see that all the fake accounts were active on the same days, on the same 3 days in this example. And every time the attacker would use the previously registered accounts to post spam content, while at the same time register the next batch of fake accounts. So this way, by having a post once every few months, the fake accounts can stay under the radar because it's really low volume. But at the same time, having multiple posts on their profile can help them look more legitimate to other users. In a more extreme attack, we also saw a few thousand fake accounts that were registered in 2012, all suddenly becoming active 3 years later, just to update their profile with this website link. And these short URLs resolve to different non-existent domains, like those listed here. And if a user clicks on all those domains, they're redirected to facebook.mobileprizes.mobi, I think, and a pop-up appears congratulating them on winning a prize from Facebook. And if they keep following along the instructions, I think they just led through a series of redirects, some attempting to try to get their Facebook login and some attempting to download stuff on their machine. So to quickly summarize, describes a brief analysis of the techniques and tools that attackers use to evade detection to create fake accounts. We show that when given a choice, the fraudsters will choose the path of least resistance, preferring desktops to mobile devices, Android versus iOS, and using older devices to be more cost effective. Also compared attacks targeting different geographic locations and different online service verticals. We show that fake accounts targeting global online services mostly come from North America and Southeast Asia, but those targeting China most come from within China. And we also saw that accounts on social networks are bigger and more automated than those on financial services, and the fake accounts also tend to sleep longer. So in any case, the fraudsters are becoming pretty good at masquerading the fake accounts and hiding their operations among the other billions of legitimate users. And our hope in its report is just to shed more insight onto the operations of fraudsters, and we hope that can inform the community as a whole. Happy to take questions.
Hi, thank you for the talk. My name is Abhishek. Two questions. One, where are you collecting this data? Second, what makes you trust, if this is an assumption on my part, are you basing this Windows and on user agent string?
So first question is where we got the data. Second question is how do I get the device info?
Yes.
Right. So we are a SaaS service, so clients upload their data into a cloud backend. Basically, we run our analytics on the cloud.
Okay.
It's a SaaS service.
Okay.
For the device information, I looked at these online services that have both a web interface and a mobile interface, and I got that from the user agent string.
And so a follow-up on that would be, if I'm an attacker, the first thing I would do is, let's say I have a Selenium or a Phantom.js job, I would put Windows string because it's most accepted by most site. Any other user agent string, most website would just block me outright. So if I go back to your earlier graph that which shows Windows is the most utilized platform, I wonder how have you correlated that data before?
Are you saying that attackers would intentionally use a Windows user agent string?
I would do that.
Why would you do that?
Because to look more legit rather than coming from Linux accounts. Like if you look at cloud services, it's more expensive to buy a Windows, rent a Windows VM. So I would just write a Linux job and masquerade the string because it's accepted mostly by everyone.
I think that would actually make you stand out a little more because most users access services from mobile devices.
I mean, again, if I'm using user agent string, then I would use a mobile, mobile user agent string.
Yeah, I guess it's possible that they could spoof it, but it's not part of the detection. And I think for them, they would just get different interface, right? The content would be different, and I don't think that I don't think that's a good way to spoof it because there are other ways that could give you indicators could give you away that you're not from a Windows box, I guess.
We can talk afterwards.
Yeah, sure.
Two questions. One was, you showed all different cloud providers. I didn't see Google Compute Engines and I didn't see Azure. And secondly, Amazon was on there a lot. Can they use your data to reduce this? Like, or is that one of their goals, is to reduce this, or is this a revenue source for them?
Well, I think the first question is whether we don't see some of the bigger players in this space, and I think this graph has the services hosting the most number of accounts, and they're not on there. And another reason is how I got this data, right? How do I know which service they're from? And Amazon provides a full list of publicly of the IP address used by AWS, so it's very easy to crawl that information. For the other ones, we have to kind of rely on third-party data or from our own research. And so we don't see as many people coming from Microsoft and Google, but it could be an artifact of that, but we try to be fair. And the other question is whether cloud services care about this. I think, to me, from my experience, they more they care more about fraudulent transactions if they don't get the money from their customers rather than what's going on in their virtual machines. I'm sure they try to do what they can, but I'm not really sure if they have the ability to inspect the VMs for what's running. And if they do, I mean, these people are just connecting to a social network. That wouldn't be suspicious, I don't think.
Okay, thank you.
So how do you know, what's your ground truth for the actual fraudulent accounts? Do the services tell you that, or do you detect them and verify with them?
Yeah, we detect them through our unsupervised machine learning approach. And yeah, our customers do take action, so we get some feedback from them. And I don't think anybody really has ground truth in this area. And so that's best we do. And then we detect it, we give it to our clients, they take action, and they give us feedback. And I think that's a pretty good loop of ground truth there. But I'm sure there are some more that we missed.
Can you talk a little bit more about the supervised learning that you do, or the success rates that you have had?
I don't think I can talk too much about it. We can talk offline if you're interested.
Okay, I'm surprised that the majority of accounts from AWS are not fraudulent based on your research.
Are not fraudulent.
Right. So like 23% are fraudulent, then most are not.
I think there are legitimate uses of the cloud. I think everybody would agree here. So not all of them are fraudulent. I know like some, there was a prepaid phone from Walmart that I remember that actually routes their data through the cloud. So not all cloud usage would be bad.
Okay, thanks.
Hi, so in terms of percentage, maybe fraudulent account maybe like 20. But in terms of, some fraudulent account, they have like very large traffic. So in terms of traffic-wise, like do you know what's the percentage for like different hosting service, roughly speaking?
Well, I'm not really sure. It really depends on the service. Like some services, they only have transaction data, and some services have like logins. They have like social interactions. Like, oh, I add a friend, I have a post, I logged in, and then mobile games have a different set of events. So it really varies. But I didn't look at it. I only look at in terms of number of accounts.
Thank you.
So when you were showing the data between US fraudulent accounts and Chinese fraudulent accounts based on where the fraudsters were and where the fraud was being committed, there was one of the providers, Colo Connect or something or other, that was like 90+% fraud. And they have to know that's the service they're providing. Can you extrapolate on that at all? Yeah, Colo Crossing, that's a pretty intense concentration of fraud going on there. I mean, they must be adding features that the fraudsters really like.
I have to guess that there must be some affiliate network going on. So Colo Crossing, I don't know how they're affiliated with other cloud providers, and it could be just a name that they use. Some of this is from whois information that may not always be reliable. If you have any suggestions on how we can start investigating it, I would be really happy to talk to you about that. But at this point, I have only the surface information about their name. I think back there is a question.
So this is regarding where you talked about, most of the US fraudulent accounts originate in US. And you also talked about how it's very easy to create VPN and proxies. So did you determine the geolocation based on the VPN IP or the IP prior to that?
So we don't have visibility into like all the path, right?
Okay.
So from the service providers, from the online service perspective, I see the last hop.
I see.
And so that's what we had to depend on, unfortunately.
Thanks. I was curious to know if you guys had done any studies on the fake news being spread by these fraudulent accounts.
We're working on it. Stay tuned.
Hi, my question is, do you see like more human-driven fraud or like technology-driven fraud, like the shadow brokers NSA leak? You know, that leads to more fraud versus like just more population leading to more fraud.
I think it's mostly like the services and what kind of features they provide that would attract fraud. A lot of the stuff we see, not all of them are very sophisticated, right? So you can just create an account and you can do whatever you want on the platform. So I haven't really seen a lot of the what you said about NSA leak or event-driven fraud, but like around holidays or around certain events, definitely there would be some type of fraud, more activity going on. Questions? Okay, thanks so much.
Hi. Hey, yeah, so I think that's it for today. Thanks for coming. The next one will probably be in a couple of months or whenever I find the next company to speak. But thanks for coming. The next, you can hang around as long as you like to with each other, to meet other people, to like, chat. But otherwise, the presentations part of the meetup is done. Once again, there's some stuff left from O'Reilly. They are having an AI conference in September in SF, and they basically are inviting all of you guys to go. I think there's a 20% off code. If you're interested, just look for me. Maybe I'll post it. But otherwise, thank you.